Right, so I'm going to talk about the architecture, which I believe can be used to implement AGI, and which I'm currently doing. Of course, this isn't final. This is just what I'm working with at the moment, and it will likely change in the future. So the key realization that I had is that you can't actually separate memory and reasoning. Like, a lot of people try to separate memory and reasoning, like you put the memory in a database or something, and you have the LLM for reasoning. But I actually think you can't separate them, because if you think about how the brain works, there's no separate memory place or no separate like reasoning module or whatever. Like, they're literally all interlinked. And an LLM is really just a neural network with some optimizations applied on top. But an LLM actually encodes all its memory within the parameters of the network. So to try and separate memory and reasoning and expect to have good inference, it's just not going to work. So for that reason, for my AGI architecture, I'm actually just going to combine both memory and inference into one sort of core. And before I explain full architecture, let me explain this core. I won't explain too much, I'll do it in a more detailed video, but this is essentially our inference engine. So imagine you have ChatGPT. This is an inference engine, right? You can just query in, ask it like a prompt, and it will give you an answer. This is an inference machine. Now, the problem with current inference machines is that they don't actually like train in real time. As in, like, if you tell ChatGPT something, it's not going to remember it, and then if you ask it later, it's not going to like recall it unless you're in the same context. But that's not really the same thing as persistent memory. That's just loading up the context window. And so this is actually the biggest challenge in AGI right now, in my opinion, is how do you achieve continual learning? So this is the biggest challenge which I need to solve. But for now, let's just imagine I have a way of solving it. So I'm just going to define what this core does, and then going to define how it actually interfaces. Not going to define the implementation. So this core is going to let you query in, so you can like send in a prompt or something, and then it will return. So this is just a standard inference call. But the next thing, like the other function, which we need to add, is a real-time reward function. So I'm going to call this a feedback function. And just like in the brain, when you go through your life, you're constantly processing events, and you're actually constantly deciding, is this event good, is it bad, should I release dopamine, all these neurotransmitters. So same kind of concept here. If you want to be able to train your memory graph or network in real time, then you need to also have a real-time feedback. So these are the two queries or functions which this core is going to expose. And then let's just define some properties which this core should have. So the first property is that we should be able to have lossless encoding. And what I mean by this is any kind of information you send into the query, it should get saved into store, and we shouldn't lose any. So if I query in, please can you check what events I have? I have a birthday party tomorrow. Then it should actually like save in whatever implementation of a memory network on top of an LLM we're implementing. It should save the information that you're giving it. That's the first property. And now the second property is going to be, well, we want, I'm not sure how to say this like in technical terms, but we want perfect inference. So what I mean by this is with all the information that you've encoded on top of the base LLM substrate, so think about like Claude Code, all of these LLM, they have some base level of knowledge in them, right? You want perfect inference with that knowledge and all of the new knowledge that you've added in. And if you can guarantee these two things, then you've essentially built a continuously learning inference machine. And this is the core of my AGI architecture. If we get this right, then the rest of the architecture should work fine. And there's also like one more property, I guess, and you want it to be like fast retrieval. So you don't want it to take ages. Can you imagine if every time you tried to think something in your brain, you took like 20 seconds? You wouldn't be able to do anything, because every single action you do has to go through the brain, and you want to make sure this retrieval is very, very fast. So these are the properties of the core. Now let's just assume we've implemented them and we have this core. Let's move on to the actual architecture. So I modeled this off the brain, and we're kind of treating, let's just define what we're actually trying to do here. So basically, let's say we have a world model of a computer system. A world model is basically like an internal model of the outside world or something, kind of like an inbuilt physics engine. So you can, as humans, you can predict like if a ball bounces off a wall, it's going to come back in the opposite direction, or if a leaf falls off a tree, it's going to like fall and hit the ground. This is a world model. It lets you basically create predictions of the future, and it allows you to reason your way through a lot of situations quite well. And so if I'm building Zoral, a digital worker, the world model in this case is basically the computer, because like the agent has access to this computer, it gets all its inputs as this computer, controls this computer. It doesn't like interact with the outside world at all, right? It's all through this computer. So this is the world model. And now let's imagine your computer is just alive. How can you make a continuously learning machine which can learn any task and do anything? So now I can explain the architecture. First thing we're going to have is the attention gate. So the point of this is just to take in all interrupts from the outside world. You could have things like a screen recording, or I'll just say screenshots now, it's easier. So these are basically your senses. Like you could have OS notifications, just any kind of senses. In humans, this would be like your eyes or your ears, the way you get input from the outside world. And the attention gate is going to query all of these interrupts. It basically asks the store, or the core, it's going to be querying, basically asking the question, is this event surprising? So see how we're using the keyword surprising? That's interesting, because a human brain is actually predictive. As in, we don't really, like, we try to predict what's going to happen, and we try to minimize our prediction error. So by asking, is this event surprising, we're essentially asking, does this have a high level of prediction error? And then if it does, that means we should probably handle it, because if it wasn't surprising, there's no need to handle it. We knew what was going to happen. So if we have a surprising event, we pass it into our processor. In like the brain, this would be like a cortex or the prefrontal cortex, which basically just processes information. Kind of like a reasoning engine, but not really. So we're going to send in surprising event. And the processor just gets an event, and then it will just query to our core, what should I do? And this is where the perfect inference of the core actually comes in that it should have all the previous knowledge that we have, and it will basically tell us, like, should we attend to this? What should we do? How do we handle this? Should we just ignore it? Just like think about as a human, when we see things that are surprising, we then decide what do we want to do with this. Sometimes you can just leave it. So let's imagine the processor then decides there's something you want to do, and this is where the motor unit comes in, or you call it like the execution unit. So the motor unit is kind of like your muscles in the human system. So when you want to do something, your brain goes and tells, well, fires through motor neurons and goes and basically instructs your muscles to do stuff, like send in a task. And now the motor unit can go and again query to the store. Query, how do I do this? And the motor unit might need to do multiple things. Like if the task is a bit big, then it can just do multiple queries, get a response, keep querying. And the idea is that, notice how we're just continuously offloading the majority of the inference work into this core. This is the idea. And this is the gap which I think a lot of people aren't doing when they're trying to build these autonomous intelligent systems. They are trying to sort of separate out the components, whereas in reality, your brain is one unified component. So you should really be offloading all of the work into one unified component. And now let's say the motor unit has actually completed this task. Well, then it just sends a interrupt or feedback back into the attention gate. Now this is actually kind of cheating because in humans, we don't have any kind of, like when your muscles are done, they don't really send a signal back to your brain saying we're done. You kind of just see that you're done by by your senses, right? I mean, this does kind of exist actually. There are some sort of results which say when you finish doing something that your brain set out, you send a result back, but this is more so just for our convenience sake, and it works pretty well in the architecture. So cool, we've got the overall flow. We take in all the interrupts and stuff from the external world, i.e. the computer, we take it into the attention gate, pass it through the processor, and then if the processor decides what to do, then it sends it over to the motor unit, and we just process it. And this is completely asynchronous, so we can be processing multiple things at a time. The processor will generally decide, should I pay attention to this or not? And again, notice how we've offloaded that to the core. The core then therefore has to judge, is this important, or is another event which I'm doing maybe a few minutes earlier, is that high priority? So we're essentially offloading all of the work into the core. And this is where, this is the importance of lossless encoding and perfect inference. If we have both those properties, then we can be sure that all of this will work. But there is one thing missing, and that is actually a reward mechanism, right? If you think about how human operates, when we do things that we get rewarded for, then it's good. We reinforce that behavior. If we do something like we put our hand on a hot fire and we feel pain, this is going to obviously cause a bad reaction, and we're going to try and stop this kind of behavior. And currently we're missing that. If we, let's say we fail in a motor unit, and then we make queries, and we send results, like we send a failure result, we don't have any kind of reinforcement loop right now, which is going to be allowing us to actually provide feedback. And feedback is crucial because it's with feedback that you can decide the best way how to structure your internal memory network. Feedback is what allows you to build up confidence in specific synapses, which allows you to make more confident decisions later, next time, which feeds into perfect inference. And so we need to actually build a feedback component as well. So I called this I guess in the brain this would be like the amygdala, but it's not really the same thing, like the emotion regulation. I'll just write this up. But we can just call this the feedback center. It's almost like a loss function as well in a sense. So every single interrupt which comes into the attention gate, we're just going to also immediately forward this to the feedback center. So everything which our system gets, every single input, we're just going to forward everything into the feedback center. And the feedback center is first going to query, was this better or worse than expected? Notice again, I'm doing it relative to what we expect. This is coming back to the idea of minimizing predictive error. This is, I mean, humans actually minimize free error, but predictive error is a pretty good proxy of what free error is. So humans are just like prediction machines, just like most models, are just trying to predict what's going to happen and minimize that error. So we're never surprised, because ultimately if you're surprised, that means something went wrong. You didn't predict something correctly, and that can lead to bad circumstances. So everything a human does is to minimize predictive error. And so we query, was this interrupt better or worse than expected? Or if it was just neutral, then that can also be a answer. But once we've got a result, let's say we get something between -1, 0, and 1, where 0 is just neutral, so the increment interrupt is neutral. 1 was really good, like let's say it completed the task perfectly and did something and got feedback from another worker, like that task was great, that's 1. And then -1 would be something like, I failed at this task, couldn't do this. That's clearly negative, we don't want to do the same kind of behavior again. So we get this feedback and we send it back into, this is where we actually send feedback back into our core. And so this feedback really just acts as a real-time loss function, which allows us to improve the internal representation of our memory, build up confidence in the walks, or I guess you could say synapse connections, which are good. And yeah, this is just allowing us to build up more confidence, and it's like a real-time reinforcement learning algorithm in a way. But yeah, this is the general architecture. In the next few videos, I'll be talking about how to implement this core, because this is really where the actual challenge lies, and everything else is kind of a wrapper on top of it. But this is the general idea: offload the majority of inference work into the central core, and these individual components are kind of just like wrappers. This actually does work pretty well, and it is modeled off how the human brain works. So hopefully we can see some good results as I improve this architecture. But let me know what you guys think.